Welcome to The Explainer. Today, we're going to talk about a really simple mathematical formula that has this wild secret history. It's a story that connects 19th century storm chasing to the huge data sets that run our modern internet.
Yeah, I know. Sounds pretty crazy, right? But the very same logic that helps recommend your next favorite song or even spot online fraud, well, its roots are in a surprisingly low-tech problem, predicting tornadoes. So let's start right there, with a story about a storm.
So, our story kicks off not in Silicon Valley, but way back in the 1880s, with a scientific dust-up that became known as the Finley Affair. And at the heart of it all was a U.S. Army sergeant who made a very bold and, well, a seemingly incredible claim.
So, Sergeant Finley's results looked amazing, almost 99% accuracy. But a geologist named Grove Carl Gilbert saw a huge flaw. See, tornadoes are incredibly rare. So as Gilbert pointed out, you could get a 98% score just by saying no tornado every single day. His simple but brilliant point showed that Finley's metric was basically useless. So to fix it, Gilbert came up with a better way to measure accuracy, a way to see if you are actually successful or just lucky.
That's a great question. If Gilbert had the idea first, why don't we know his name? Well, it is a perfect case of what's known as Stigler's law of eponymy. It's this kind of funny, ironic rule in science that says, no scientific discovery is ever named after the person who actually discovered it first. And this is a textbook example.
So fast forward about 30 years from that whole tornado debate. A botanist, Paul Jaccard, who has no idea about Gilbert or his work, rediscovers the exact same mathematical idea. He was just using it to compare plant species on different mountains. He published his findings, his name was the one that stuck, and bam, the Jaccard Index was born. But that core idea came from needing to separate real skill from just statistical noise.
Okay, so how does this idea actually turn into the simple but really powerful formula we use today? This is where you can see just how elegant it really is. At its heart, the formula is just this: intersection over union. You take two sets of things, it could be anything, musical tastes, grocery lists, whatever, and you divide the number of items they have in common by the total number of unique items across both sets. That's it. It's this beautifully simple way to get a score from 0, which means no similarity at all, to 1, which means they are identical.
Let's make this super concrete. Say we want to compare two tech enthusiasts. Person A likes Reddit and Hacker News. Person B likes Hacker News and Stack Overflow. Their intersection, the thing they have in common, is just one item, Hacker News. Their union, all the unique things between them, is 3 items, Reddit, Hacker News, and Stack Overflow. So we just take the size of that intersection, which is 1, and we divide it by the size of the union, which is 3. That gives us a similarity score of about 0.33, or 33%. It's simple, it's clean, and it's incredibly effective.
Okay, so that's a neat little formula, but what do we actually do with it? Well, this simple ratio turns out to be this fundamental tool, kind of like a Swiss Army knife for similarity, across a ton of different and really fascinating industries.
Here's a great example of its power in cybersecurity. Security experts can take the code of a website and break it down into these small, overlapping pieces called shingles. Then they use the Jaccard Index to compare these sets of shingles between different sites. So even if hackers change the text or the layout a little bit, the underlying code structure often stays very similar, and this method lets them find and cluster all these malicious websites together.
And in the world of data science, data is often just a mess. You might get two spreadsheets where one column is called user_ID and another is just user ID. To a computer, those are completely different. But by treating the column names as sets of characters, data scientists can use the Jaccard Index to automatically find columns that are highly similar, which saves countless hours of manual cleanup.
It's also helping to drive scientific discovery. In chemoinformatics, which is basically the science of chemical information, the index is used to compare the digital fingerprints of different molecules. This lets researchers instantly search these massive databases for compounds that have similar structures. And that is a crucial step when you're developing new drugs and materials.
But as powerful as it is, the standard Jaccard Index isn't perfect for every single situation. It has one really crucial weakness, and it shows up when the sets you're comparing are wildly different in size.
Okay, so here's the problem. Imagine you're searching for Ontario, Toronto. If you compare that to a small list of Canadian provinces, the Jaccard score works really well. But what if you compare it to a massive list of global locations that also contains Ontario and Toronto? The score plummets because the union, the total number of unique items, becomes enormous. So for finding if a small set is contained within a larger one, we need a little tweak. It's called Jaccard set containment. This version divides the intersection by the size of the smaller query set, and it effectively ignores the size of the larger.
This distinction, this difference between similarity and containment, becomes absolutely critical when you scale things up, when you're not just comparing two people's preferences, but trying to find relevant information across the entire web.
I mean, just look at this number. That's how many different domains, or sets of data, were found in just one web table collection from back in 2015. Over 262 million sets. And the web is only gotten bigger since then.
The real challenge is that the size of these datasets isn't uniform. It follows what's called a power law distribution. And what that really means is you have a few gigantic sets with millions of items, and then this massive long tail of very small sets. Trying to run a simple Jaccard comparison across all of them one by one is, well, it's computationally impossible. The solution is a system called LSH Ensemble. Instead of comparing the entire massive sets, it does something really clever. It creates a small, efficient sketch, like a CliffsNotes version of each dataset, using a technique called hashing. But crucially, it first sorts all the data by size into different buckets, small, medium, and large. By comparing sketches just within the right buckets, it can perform these lightning-fast searches. We're talking under 3 seconds across hundreds of millions of datasets.
It's really an incredible journey for one powerful idea. It started as a way to validate tornado predictions, and it evolved into a fundamental building block for navigating the immense complexity of the modern internet.
So the next time your feed recommends something you actually like, you can thank a 19th century geologist and a Swiss botanist. It really leaves you wondering, what other elegant, fundamental principles like this one are hiding in plain sight, secretly powering the digital world all around us?